In this presentation, we are going to look at some remaining matters, outstanding matters even, regarding the gamma distribution. So one quick thing is that the sum of two independent gamma variates, two observations from the gamma distribution, the sum of those two gamma variates is also a gamma variate, so it's also a gamma distribution, something from the gamma distribution. So let x1 and x2 be two independent gamma variates with parameters alpha 1 and theta for the first one, and then alpha 2 and theta for the second one. Then what we're interested in is the sum of those two, alpha x1 plus x2. Okay. So what we're going to do is use the moment generating function approach to sort of demonstrate this. So the moment generating function of y of t, that's equal to the expected value of e to the ty. Okay. Now y is the x1 plus x2. So what we get here is the expected value of e to the power of t times x1 plus x2. Now, using the rules of powers, essentially what we could say is that is equal to the expected value of e to the tx1 times e to the tx2. And we could break that up into two independent expressions there. Okay, the expected value of e to the tx1 times the expected value of e to the tx2. Okay, and essentially what we have there is that it is the moment generating function of both of the original gamma variates separately, m of x1t times m of x2t, and when we get expressions for those, now this is the how we would express the moment generating function, the MGF of each of the two variates. In the first case, it would be 1 minus theta t to the power of minus alpha 1. Okay, so that's just the general shape of the MGF for the gamma distribution. Likewise, we multiply that by 1 minus theta t to the power of minus alpha 2. And again, we just use the power rules there. Okay, and we end up with this expression here. Now this is the MGF of the moment generating function of a variable, gamma variate, if it had the parameters alpha 1 plus alpha 2 theta. So therefore we could sort of say that, you know, this here expression y equals x1 plus x2 is also a gamma variate with the parameters alpha 1 plus alpha 2 and theta, because it ends up with this moment generating function. Just sort of how we would demonstrate it. Now, this is a sort of tricky thing, and I'm just going to I need to mention it, but I'm not going to go into it in too great a detail. The moment generating function of a gamma distribution is as follows. K of xt is equal to minus alpha times log of 1 minus lambda t. Okay, now just as a quick remark, this is based on the fact that I'm using the moment generating function of a gamma random variable. It has this expression here. Okay, so I'm just sort of using this as a sort of something we already know and that we're going to base our answer on. Okay, so this is the general expression for a cumulative generating function. It's log of e of the moment generating function m of xt. Okay, so it's log of e log to the base e of 1 minus theta t to the power of minus alpha. Okay, so we have a minus alpha there. Okay, to the power of minus alpha. So using log laws, that's what we get there. Okay, now that's really all we were needed to do, but we can go further with this. Okay, so the log of 1 minus a can be expressed as equal to minus a plus a squared over 2 plus a cubed over 3, and so on. Okay, so using that, we can express this expression here as alpha times theta t plus theta squared t squared divided by 2 plus theta cubed t squared divided by 3, and so on. Okay, now what we can also do is each of these expressions here. Okay, so we can express them as follows here. Alpha well, basically these parts are broken up as follows. Okay, so what we can do is re-express this as each component term as t to the power of r times t to the power of r, now times the factorial of r minus 1 and divide that by r factorial, where r is the index. Okay, now that sort of seems a very strange thing to do. Why do we need to do that? It's just r. Okay, r, the factorial of r minus 1 divided by the factorial of r just gives us r. So why do we make this complication? And there's a good reason for it. Okay, so essentially what we want to do is find out the rth cumulants of a gamma distribution. Okay, so it's essentially each of these cumulants are what we're called small k, or sometimes it's kappa, and they're the coefficients of t to the power of r divided by r factorial. Okay, so this is a standard result that we're going to require. Okay, so what we can do is break that out. So it's the coefficient of t, what is it actually? Theta r and r divided by r factorial. Okay, so what we are left with is this part here, t to the power of r times r minus 1 factorial. So those are the coefficients of those expressions there. Okay, so that's going to be handy going forward. Now I'm going to sort of stop the video there really, because these are what the coefficients will give you. K1 equals alpha times theta, which is the mean. K2 is alpha times theta squared, which is the variance. K3 and K4 and so on, they can be used to find the coefficient of skewness and the coefficient of kurtosis. Now, there's a little bit of work here to be done, and this is sort of based on these things called standardized moments. And I'm getting very far ahead of myself there. Just to remark that we can use this expression here, K3 and K2, to come up with the coefficient of skewness of the gamma distribution. Okay, and likewise mu4 and mu2 squared to come up with the coefficient of kurtosis. Now that's how you would deduce them there, but that's going very far beyond what we need to do here. I'm just sort of setting it up, but there's a lot to do here about how you would use the coefficient of skewness and kurtosis. Essentially, there's a lot to do here first before we continue on. So the main way to do it is look at these things, and I'm going to do that in a separate video. But just this sort of just dovetails with that. Alright, okay, we'll leave it there.